So we have learned how to update each of these weights in a gradient descent like setup, but there is a very interesting software engineering trick or a trick in computer science called memoization. Remember, it is memoization. This is not a spelling error. It is not memorization. It is memoization. Let me explain why we need memoization. And some of you who have studied computer science, okay, some of you who might have studied a subject called design and analysis of algorithms, right? If you have studied algorithms subject, in this subject in computer science, of course, if you're a non-computer science student, you probably would have never encountered it. But those of you who are computer science students would encounter this subject called algorithms or design and analysis of algorithms. That's what it's called in some universities and colleges. In this subject, you will come across a concept called dynamic programming, right? Dynamic programming is a super duper powerful programming method, not a programming, it's a very neat algorithmic technique. At the core of dynamic programming is this idea of memoization. Okay, so those of you who studied computer science and specifically algorithms would encounter memoization in the area of dynamic programming. If you have not studied computer science, don't worry, I'll explain you what memoization is and why it's useful and even why is it needed in the first place. That's very, very important to understand, right? Names don't matter. It is the concepts that matter. It is the need of the concepts that matter. So let's go step by step. These are a W3 weights, right? So in my big network, I've redrawn my network here. Okay, so first let's assume I'm trying to update these two weights. When I update these two weights, I will compute, of course, I'll compute these two derivatives. Now when computing these two derivatives, you'll notice that the derivative that I'm computing here, right, the same derivative I'm recomputing again. So first, let's assume, first I will update W311, then let's assume I'm updating W321. When I compute the derivative of L with respect to W311, I'm computing this ratio, or sorry, not ratio, this derivative value, which is derivative of L with respect to O31, but I'm recomputing the same thing again when I'm again updating my W321. Instead of computing this two times, what if I compute it once and reuse it? So the core idea here is compute once and reuse, right? You can see here in the computation of W311 and W321. Now let's look at it in the case of W211, W221 and W231, right? Here also you'll see derivative of L with respect to O31, which is exactly the one that you have here. Okay, so let's assume first you update these two weights, then you come to the next level and update all the weights in the next level, right? So whatever derivative that you computed here, whatever derivative that you computed while updating W311 and W321 can again be used when you're updating W211. The same weight, the same derivative is also here. The same derivative is also here. So there are 5 places just in this in this small subset of cases that we have seen here. If you compute it once, you can reuse it here, you can reuse it here, you can reuse it here, you can reuse it here and reuse it here, which is super useful. And if you notice, right, even here you can reuse it. Even when you're updating any weight in the first layer, which is W111, even here you can use it. So you're reusing it again here. Similarly, when you update W112 or W113, all these cases you'll again encounter this derivative. So you can reuse it many times, right? So the core idea of memoization is this. The core idea of memoization is this. If there is any operation, right? If there is any operation, right, that is used multiple times, that is used many times, repeatedly, right, then it's a good idea to compute it once, then store it and reuse it. That's all is the concept of memoization. right? And this is staring at our face here, right? Because once you compute derivative of L with respect to O31, you can reuse it like many times. Similarly, look at this. Look at W2 weights. If I compute this derivative of O31 with respect to 21, I can reuse it here. I can reuse it here, right? I can reuse it here. I can reuse it here. So this is, I can again reuse it here. I can again reuse it here, right? So even not just derivative of L with respect to O31, if I can compute derivative of O31 with respect to O21, here I'm able to reuse it again, right? So in this diagram, there are some derivatives that if we compute and store, right, we can reuse them so as to reduce the computation, right? Because computing these derivatives is not trivial, right? It takes some time. So if you just compute it once and store it, right, you don't have to compute it, what will memoization result in? It will result in a very good speed up. It will speed up your code. Of course, it takes slightly more memory. It takes slightly more memory because you're storing these derivatives, but it will speed up enormously, right? Because instead of computing 20 times, right, or maybe 100 times in some cases, you're only computing it once, right? So let's write it down, right? So what we can do it as follows. At this node, right, at this node, I can store something like this. At this node, I can store my O21, right, impacts my O31. My O31 impacts my L. So at this node, I can compute derivative of L with respect to O31 and store it here. So whenever I put anything in a box, what I mean to say here is I compute this. So this impacts this. So I compute this derivative, this function, right? And I store it here. If I store this derivative here, it becomes much more efficient when I have to use it to update all of my weights. Isn't it? This value, suppose it has a value of 2.4 in some iteration. Okay, if I compute this value and keep it here, right, I can reuse this 2.4 value when I'm updating all other weights, right? So at F31, I will store this. So what about here? Here, the output here is O21. O21 impacts O31. So I will store derivative of O31 with respect to O21 here. So what do I store here? My output here is O22, which impacts O31. So I will store derivative of O31 with respect to O22. And if I store it here, because this derivative is useful everywhere here. Okay, let's look at it. Where is derivative of L with respect to O31 useful? In all the weights. But where is derivative of O31 with respect to 21 useful? It's only useful for weights which are in this level. All my W2 weights. Because this derivative does not impact my W3 weights. That's why I'm storing it here, right? So whatever I store here is useful in all the layers before that. Whatever I store here is useful in the layers which come before that, right? So what about here? Okay, so what about here? Okay, let's see. Here, my O13 impacts my O22. It also impacts my O21 because look at this. My O13 goes through this path and impacts O21. My O13 goes and impacts O22. So I will store two derivatives here. My first derivative is O22 with respect to O13 because my O13 goes and impacts O22 because of this impact. I'm storing this because this also goes and impacts, right? This also goes and impacts this through this chain. I will store derivative of O21 with respect to O13. So here I'm storing two derivatives because this output goes to two cells. Here I'm only storing one because this output only goes to one value. Here I'm storing only one value because this output goes to only one value. So if an output from a function, so what do I store here? Let's see an example again. One more example, right? My O11 goes and impacts O21. So I will store derivative of O21 with respect to O11. My O11 will go and impact O22 again, right? It also impacts O22. So I'll store derivative of O22 with respect to O11. And both these derivatives are required in all the levels below this. And you can see that here, right? You can see this here. So what are the derivatives? O22 with respect to O11, O22 with respect to O11, O22 with respect to O11, right? So if you store it and keep it here, so these derivatives that you are computing here are useful for all the weights that are there in the previous levels. So if you compute a derivative like this or an operation like this and store it, it will be useful in reducing the time it takes. And how many derivatives are we storing here? We are storing one derivative, 2, 3, 4, 5, 6, 7 values. There are only 7 values that you're storing. So the memory is not a lot, right? Actually, slightly more memory. I think that's a fair thing to use. For slightly more memory, you get huge speed up, right? Because you're only storing 7 values, but the amount of computation that you're reducing is massive, right? Imagine this derivative is used by all the 20 weights, all the 20 weights that you have, because you have 12 weights in this level, you have 6 weights here, and you have 2 weights here. 4 into 3, 12, 3 into 2, 6, 2 into 1, 2. So all the 20 weights here need you to compute this. So instead of computing it 20 times, you computed it only once, and it still is reused 20 times. This technique is called memoization. So whatever we discussed right now, right, what did we do? We simply applied chain rule and we used memoization, right? What did we do? We just used chain rule of differentiation, and we used memoization as a trick to avoid recomputing the same thing. So when you apply chain rule and memoization, the algorithm that you get is called back propagation. One of the most important and one of the greatest works probably in the whole of machine learning. But at its core, it's very simple. It's chain rule plus memoization. Okay, we'll understand more details about back propagation in the next video from an algorithmic standpoint. We understood the mathematics here, right? So the chain rule is the math part, right? The memoization is a computer science trick to make your computation faster while increasing your memory slightly, right? Very, very neat idea. And as I told you, memoization is a very, very important trick in the design and analysis of algorithms. If you ever learn design and analysis of algorithms, memoization is one of the most important tricks in probably whole of algorithmic design, right? So we'll explain backpropagation in more detail in the next video, but backpropagation in a nutshell is nothing but chain rule plus memoization. If somebody asks me, what is backpropagation? I would say it's a very, very simple mathematical trick of using chain rule of differentiation with memoization. That's all it is. Okay, with some, of course, with some optimization sprinkled in. Okay, because you have gradient descent, because you're using the chain rule to compute derivatives, those derivatives go into computing a stochastic gradient descent or something like that, right? So it's, in a nutshell, the two greatest ideas in backpropagation are chain rule and memoization.